decrease, no? Because the total is constant. So if one is increasing, then other has to decrease. So elastic strain is decreasing. Initially, suppose the strain is so that it doesn't cause yielding. So suppose this is 0. Okay? So then whatever strain you have here is elastic. Complete elastic. Because time is 0. There is no creeping. Right? Creep strain will develop with time. Okay? So as time increases, then creep develops. And this will become asymptotic. Right? So at a very long time, the creep strain is going to be equal to total strain. Something will go to 0, which is starting from here, and that has to go to 0. And at every point, the summation will be, the two summation will be equal to this, and that will be constant. Is it making any sense to you? No? Yes?
इलास्टिक स्ट्रेन कम हो रहा है
इसका क्या मतलब है? बताओ क्या मतलब है? क्योंकि टोटल तो कांस्टेंट करना है,
तो कांस्टेंट है,
क्रीप स्ट्रेन को बढ़ना है टाइम के साथ, है ना?
हम तो ये तो समझ आ गया कि ये कांस्टेंट
रहने के लिए so now you are saying that now elastic strain is also behaving as a time dependent way.
Yes.
But elastic strain is not time dependent. So why it is happening? So,
sir, creep is defined as stress relieving.
Yes.
So stress, if a stress relieves, then elastic strain has to decrease.
Yeah, but he is saying that now you are making elastic strain time dependent. It's not a time dependent phenomena. So why it is showing a time dependent phenomena? This is what he is asking. You take a piece of chocolate, apply a little bit of elongation to it, very little, don't break it, and then put it in outside. What will happen to the sample? It will break, right? So in this case, the modulus which you get between stress and strain is called creep modulus. Okay? And in this case, what you get as a modulus between stress and strain is called relaxation modulus. Okay? So in this case, strain is a function of time, and in that case, stress is a function of time. And because these two are function of time, you get the modulus time dependent. So elastic strain is not really time dependent, the modulus is changing. The stiffness of the material is changing. Okay? And these kind of tests are done, displacement control tests are also done. Also in metals, but less in metals, more in polymers. Okay? The other question was, so this is okay, right? I don't know if you understood or not. Did you understand?
Yes.
So the next question was that what will happen if we do a displacement control test when we have a crack in the system? तो इसका verbal answer बताइए. Can we do displacement control test? If we can do, what will be different? Or what will happen? What will happen?
Sir, I have one doubt.
Assignment का marks कर.
Sir,
Do you have any answer?
Yes.
So then tell.
सर कांस्टेंट डिस्प्लेसमेंट जब हम रखते हैं,
हाँ.
तो उस केस में जब हम कांस्टेंट लोड रखते हैं पहले, जैसे इसमें क्रीप में हम काउंटर वेट लेते हैं बेसिकली, तो उस केस में क्या है कि हमारी जो इलोंगेशन होती है उसको हम रिकॉर्ड करते हैं, जो सैंपल में हमारी इलोंगेशन होगी। और कांस्टेंट डिस्प्लेसमेंट में जो उस डिस्प्लेसमेंट को मेंटेन करने के लिए हमारा लोड है, हम उसको
ये तो कन्वेंशनल क्रीप टेस्ट की बात हो गई, मैं क्रैक की बात कर रहा हूँ। नाउ वी हैव क्रैक इन द सिस्टम। इन दिस केस वी डू बोथ काइंड ऑफ टेस्टिंग, ओके, देयर इज नो हार्म इन डूइंग डिस्प्लेसमेंट कंट्रोल और force control. So in one case you will be measuring strain, another case you will be measuring force. That is all right. Once we have a crack in the system, then what should we do? Should we do a force constant test or displacement constant test? So force, stress cannot be constant in a crack sample. That we cannot achieve ever, okay, because there is a crack. So what should we do? Should we do force constant or displacement constant? If you have both of the options, which one you will do and why?
So जो फ्रैक्चर में आपने बताया था उसके अकॉर्डिंगली अगर देखें तो आपने कहा था कि वो कांस्टेंट लोड अगर हमको अचीव करना है तो उसके लिए अगर हमारा ऑपरेटर्स सूटेबल नहीं है कि हमारा उसको अचीव करने के लिए कई बार क्या होता है कि ऊपर ही चला जाता है वो,
तो इसलिए हम डिस्प्लेसमेंट कांस्टेंट लगाएंगे,
डिस्प्लेसमेंट करते हैं।
दिस इज योर आंसर।
पर कांस्टेंट डिस्प्लेसमेंट अगर हमें करना है क्योंकि ये बहुत ज़्यादा टाइम के लिए करते हैं तो आसान तो यही है कि काउंटर वेट का करें, हम काउंटर वेट लगा के, क्योंकि उसमें जो हमारा कंट्रोलिंग मैकेनिज्म है वो ज़्यादा कॉम्प्लेक्स नहीं होगा, उसमें बस हमें काउंटर वेट लगाना है और इसकी एलोंगेशन देखनी है कितनी स्ट्रेन आ रही है।
डिस्प्लेसमेंट कंट्रोल में भी बहुत आसान है, you just have to stretch the frame, put a hook there, that can also be mechanical, कि वो तो नहीं स्ट्रेच करे, उसके ऊपर रॉड जाएगी नहीं, फिक्स कर दिया वहाँ पे। ये सैंपल है, इसके 2 मिलीमीटर स्ट्रेच करके फिक्स कर दिया, टाइट कर दिया उसको। There can be another method, okay, where you put a bolt here and tighten it by 2 millimeter. तुम बताओ क्या करोगे? डिस्प्लेसमेंट कंट्रोल करोगे, फोर्स कंट्रोल करोगे?
फोर्स कंट्रोल सर।
क्यों?
सर डिस्प्लेसमेंट कंट्रोल में क्रीप के साथ साथ सर जो लोड वेरिएशन है वो हम मतलब इजी नहीं होगा प्लॉट करना।
सर लोड कॉन्सेंट
क्यों?
सर क्रीप बेसिकली टाइम डिपेंडेंट डिफॉर्मेशन है। अगर जैसे डिस्प्लेसमेंट ही कांस्टेंट कर दिया तो मतलब टाइम डिपेंडेंट स्टडी करना डिफिकल्ट होगा कंपेयर टू।
बहुत क्या बोल रहे हो, इसका आंसर तो क्लियर नहीं है। इन डिस्प्लेसमेंट कंट्रोल में अगर क्रीप टेस्ट कर सकते हैं तो क्रीप क्रैक टेस्ट क्यों नहीं कर सकते? उसमें क्यों क्रीप नहीं मिलेगा हमारे को? I will measure what is the force coming on the sample. What will be the difficulty? आप बताइए।
सर फोर्स कंट्रोल करना चाहिए।
क्यों? मेजॉरिटी इसलिए
मोस्टली वही किया हुआ है।
पर क्यों किया हुआ है? क्योंकि वैसे ही मशीन बनती है।
सर कांस्टेंट लोड कांस्टेंट स्ट्रेस पे ही जनरली देखा गया है क्रीप टेस्ट में।
नहीं, कांस्टेंट स्ट्रेस पे तो क्रैक टेस्ट नहीं कर सकते।
क्रैक टेस्ट नहीं कर सकते।
क्रैक वाली बात कर रहे हैं तो उसमें कांस्टेंट डिस्प्लेसमेंट टेस्ट क्यों नहीं कर सकते? ये क्यों नहीं करना चाहिए? क्यों नहीं करेंगे? क्यों नहीं करते हैं लोग? कर सकते हैं कि नहीं कर सकते?
बिकॉज सर अगर डिस्प्लेसमेंट दिया इनिशियल डिस्प्लेसमेंट तो क्रैक रीजन में ऑलरेडी वो प्लास्टिक डिफॉर्मेशन आ जाएगा।
हाँ, आ जाएगा। फिर वो तो
सर
फोर्स देंगे तो भी आएगा।
सर टाइम डिपेंडेंट, बट सर फोर्स देने पे सर उतना हो सकता है। हाँ तो
नहीं, उतना नहीं, both of them are equivalent. So I am applying the same amount of force which will cause same amount of deformation for the displacement I want to apply. So now which one should I choose? Displacement or force? नहीं पता है.
सर आइसोलेटेड क्रीप की स्टडी अगर हमें करना है
हाँ.
तो हम सर डिस्प्लेसमेंट कांस्टेंट कर रहे हैं तो उसमें क्रीप फिनोमेना अकेले नहीं हो रहा है तो इस वजह से स्टडी इतना इजी नहीं
क्यों?
होगी।
क्रीप फिनोमेना के अलावा और क्या टाइम डिपेंडेंट हो रहा है?
सर डिस्प्लेसमेंट कांस्टेंट रख रहे हैं,
रख दिया.
सपोज 0.1 mm पर सेकंड हमने डिस्प्लेसमेंट रेट दे दिया, तो सर ये टाइम डिपेंडेंट फिनोमेना कहाँ रह गया?
क्यों? फोर्स भी तो तुम किसी रेट से दोगे ना.
सर फोर्स कंट्रोल तो हम नहीं कर रहे।
The initial stage when you are applying force or displacement, in both cases you will take some time. 2 मिलीमीटर डिस्प्लेसमेंट लगाना है या 600 न्यूटन या 6 किलो न्यूटन का फोर्स लगाना है. In both cases machine will go from 0 to 6000 Newton. That part is done. Once you apply the load or displacement, then you put the sample inside the furnace, switch on the furnace, let it go to the temperature, then thermal expansion will take place. Okay? And after that you start counting your time. Now tell, अब creep क्यों isolated नहीं कर पाएंगे? Instead of plotting strain, in this case, we can plot stress. There, what do we have to plot? That I do not know. But ऐसा क्यों नहीं कर पाएंगे? चलिए ठीक है, आप लोग एक पेज का रिपोर्ट लिखिए इस पे, और कुछ भी वेग नहीं लिखना है. You have to cite from the research article. You have to first find the research article where displacement control tests for creep crack are done. पहला तो यही असाइनमेंट हो गया अच्छा खासा. तुमको मिला है कोई पेपर जो तुम कर रहे
तो
हो?
ट्राई किया था एक बार हाइड्रोलिक।
नहीं मिला ना.
लोड एंड स्ट्रेस का ही है जितने भी पेपर, मतलब अगर
अरे मैं अगर कह रहा हूँ आपको करने के लिए तो होगा, इसलिए कह रहा हूँ
हाँ
ना,
वो तो हो गई
है ना. तो ढूंढो और
आइडिया
ढूंढ
ने
के
ट्राई
फिर
किया।
लिखो कि क्यों नहीं कर सकते. उसमें ऐसा कुछ लिखा हुआ नहीं है. अगर मिल गया
क्यों नहीं
आपको
कर सकते
article,
वो नहीं पता।
so then you will not find the answer there, that why it is not done. But try finding in the literature. Maybe I have not seen, maybe there are more articles, maybe there is something where the reason is written. Okay, so you'll have to explain why it cannot be done or why people don't do it if it can be done. Okay, so in our cracked specimen we have seen that we have two different parameters, K and J, and using this we have found out the fracture toughness parameters. Okay, so as long as the deformation zone follows what we followed in plane strain fracture toughness testing, so as long as it is smaller than, so that the theory of elasticity is valid in majority of the volume of the specimen, then stress intensity factor can be used to characterize the property of the material. Okay, so K is valid as long as the deformation zone is small. Alright, what about J? Can we apply J in creep testing? So for that you will need to remember what J is. Okay, this is J. Right. So can we apply J? What was the condition for J to be valid, and what was the condition for J to be path independent? The advantage of J integral was that it is path independent. Okay, so do you think it will be path independent in this case? Why not?
So creep modulus will change. So it will not valid. J integral will not be valid.
Why?
Because The temperature, because of the temperature effect, sir.
Because of temperature is constant during the test. So except time, nothing is changing. You are noting down the assignments, no?
Yes, sir.
Okay. So J integral was path independent. Any line integral is path independent when you have this kind of scenario. You have got dr, and this will be equal to 0 for a closed loop, for a cyclic loop, when you don't have anything inside, and this f has to be a derivative of a potential. So then it makes it a conservative field, meaning that this has to be a single-handed function of R. Okay. So in our J integral, stress and strain are two variables, and stress has to be a single valued function of strain. If this is true, then you apply the line integral and J is path independent. Okay. But in case of creep, stress is not only a function of strain, but it is also a function of time. Some hint is there maybe, and if you write reverse, then it is not only a function of stress, but it is also a function of the rate of stress. So here you can write creep strain rate. Okay. Whether they are separable variable or not, that's a different question. So I may have to write it like this. Okay. So in this case, it is not following what is required for a path independent line integral. Okay. So what can we do is that if we follow a steady state condition, and what happens in a steady state, strain rate is defined in this way. Okay. So for a constant temperature, you can write it as this. So it is not a function of, so it's only a function of stress, isn't it? Right? So when this happens, then you can probably define a new integral where you will have to use strain rate instead of strain, because we are not getting a relationship between stress and strain as a single value function, but we are also we are getting a function which is between strain rate and stress, not between strain and stress, like Rambert-Gosgood equation. Okay. So if this is true, then we can define an integral, and our reference integral is that. So there we have W, which is strain energy density, and W is defined as like this, right? So here we have to define another integration, which will be from 0 to d epsilon dot sigma dot d epsilon dot, right? And then instead of W, we use W dot. Okay. And then we keep other things same. So if W dot is a function of x and y both, then you should write this minus traction, and then you have del u by del x, and u is time dependent, so you will have to take the rate of that. Okay, so then you make del u dot by del x, and then you take that integration along the small element of the line, and this becomes a new integral, and this should be path independent. Why? Because this and this will always give you one value. So for one value of strain rate, you will get one value of stress, and vice versa. Okay, so this is designated as C star, a new name. C for creep, and star because it is shining like anything. Okay, so this is a path independent integral, and it can be applied to calculate what? So K can be used to calculate stress intensity factor, but the idea originated, K was not derived to calculate how much stress is getting intensified. K was not derived with that objective. K was a byproduct when what are the stresses in presence of a crack according to theory of elasticity was being derived by various researchers. Okay, so there was a factor which was common when you describe sigma xx, sigma yy, sigma xy. In all those functions, there was a function which was dependent on the angle which it is making from the crack tip. Okay, so if this is r and this is theta, then sigma ij, so sigma xx was also found to be this, and sigma yy was also similar, sigma xy was also the same. Okay, so k by root over 2 pi r, that thing was always there. So from there this stress intensity factor parameter came. It was not really the objective to find out k, because nobody knew that there will be one value which will be common in describing the stress. So the objective is to describe the stress and strain field as close to the crack tip as possible. Then plastic zone developed and it became bigger, so this theory was not valid, so then became a line integral, and this line integral, which is J integral, can be used to describe stress and strain at the crack tip in the plastic zone. Okay, so there sigma ij is a function of J and root r, and then you have an integration function and some other function, and then it is a, and then you have a theta function there. And similarly strain was a similar function of 1 by n plus 1. So when we use J integral, then these two equations tell us what is the stress and strain in the plastic zone, and these two are obtained by using Ramberg-Gospel equation. Okay, now what will happen in creep? In creep we have this new integral, this is path independent, and this has a relation with stress and strain rate. So this must also be defining stress and strain rate as a function of C star. Okay, and R and IN and all those things will be there. The exponent will be same in both cases. So C star is also fulfilling the objective of describing stress and strain when the deformation zone is time dependent. J is defining stress and strain when deformation is plastic, not time dependent. And K is defining stress and strain when things are elastically deformed. Right? But apart from that, K is describing how much stress is getting intensified. J is defining also, apart from defining the stress and strain, it is also defining that how much energy is released per unit crack length. Right? What is C star defining? So if J can define that this much energy is required for a unit crack growth, then it is defining the energy requirement, so energy release rate. But what is C star defining? If J is the energy release rate, J is the energy release rate, right? And what will happen if you apply J in time dependent deformation? What will happen? What wrong will I do? It will not be path independent, fine. Okay, so I fix my path. I will take one contour and I want to calculate the integral for that. Then what will be the problem for J integral? That J integral must be defined with time, because that will become time dependent. Right? Because either stress or strain will be time dependent, or both will be time dependent. So J also will be a function of time. Okay? So what does J mean? J means energy release rate per unit extension of crack. And this amount of energy, which is required for the crack to go by a unit dimension, will be different if you load it for different times. Okay? So if you load a sample at constant load, so force is constant and the displacement develops, and the initial crack length is A, and then you have another sample for which the crack length is A plus delta A. With time this is happening. Okay, so it means that for two different samples or for the same material, from going from A to A plus delta A, if you apply different forces, it will not give you same amount of energy release rate. Or if you load it for different times, it will not give you the same amount of energy release rate. Okay, so J becomes time dependent. If J is time dependent, then rate of change of J integral must be defining the rate of change of energy release rate. Energy release rate, rate of that. Okay, so a lot of rates are coming.
Power release rate.
This was strain energy density. Now it has become strain rate energy density. It is also called stress power. Okay. So dJ by dt will be defining the rate of change of crack extension energy release rate. Okay. So J has been defined as 1 by B del U by del A. So that rate is not with respect to time. That rate is with respect to crack extension. And the another derivative is with respect to time. Because there it was not time dependent, here it will be time dependent. Okay, so this quantity will now be a function of time, because U will be a function of time. Okay. So the amount of energy which is released when you go from A to A plus delta A, that will be different if you load it for different times. Okay. So per unit time, that must be defining that rate. So do you think this and these are equal? Do you think C star is equal to dJ by dt?
U dot should be there.
Yeah, that is J. When you take dJ by dt, U dot will come.
Then that will be equal to C star.
Okay. But C star I have not formulated in that way so far. So you should compare, when I'm saying dj by dt, you should compare that definition and this definition, not that one. I have not defined C star in terms of U. So look at that line integration expression and this expression and then tell dj by dt, will that be equal to C star or not? Yes or no? 50-50% chance. Tell.
Sir, no sir, it will not be equal.
No. You?
No, sir.
You?
No, sir.
Why?
Sir, because there is rate W dot is coming and there is dA. So divide by dt if we are doing then.
Okay, good. So first of all, there are a few things which you need to understand. That strain energy density is described like this: 0 to d epsilon sigma dot d epsilon. Okay. In this case, stress can be expressed as a function of strain, right? So if we plot stress and strain, which is something like this, then this represents what?
Area.
The area under the curve until it reaches a value of d epsilon strain, right? So I don't know why I have written d epsilon. I can just write epsilon, because then I will have to write d epsilon. Okay. So this will be the area under the curve. Okay. And W dot I have defined as 0 to epsilon dot sigma d epsilon dot. So what is this?
Area between stress and strain rate.
वो तो बहुत easy हो गया. So if you find out really dW by dt, what will you get? If we have to do the derivation of this thing, then what do we do? What should I do? Tell. Should I write d sigma by dt
Yes, sir.
into d epsilon plus sigma
D epsilon.
d of d epsilon by dt? Right? So if strain rate, so one thing is pretty clear, that this not always is equal to that. The derivative of this is not always equal to that. Then you also have this term. So here first of all you will have another two terms coming. So you will have dy by dt also, right? But is y a function of time? So then you will have those two terms coming, right? What about this? T is sigma dot n. So you have one of these term and one of this term. So you have del u by del x and ds. Okay. So now you will have to, if you do the differentiation of this with respect to time, you will get to another term. Okay. So you see that the derivative of this is not going to be equal to what you are getting in C star, where you have only two terms. Okay, you don't have the term where the derivative of traction is taken, where the derivative of sigma is taken. That term is missing. Okay, so these two quantities are not same, therefore these two quantities are not defining the same thing. Maybe in special cases they do, when the additional terms will have no meaning. Okay, so when you have cases where d of d epsilon by dt is 0, in that case you will have only first term, which is this, right? But this is not here. Okay, so when stress is constant with respect to time, only then you will get only the second term, and then that will come. So when stress is constant, only then this, so derivative of this will be equal to that. Only when stress is constant. Okay, so we have this new integral and we don't know what it is defining. And this is valid only in this situation. It is path independent. Okay, so this is similar to Ramberg-Osgood equation in elastic plastic case, where we define J integral. Okay, so there is an analogy between strain and strain rate. You have an equation of strain versus stress, and you have an equation of strain rate versus stress, and then with that analogy you define a new integral. So this was proposed by Hoff. Okay, and these equations were discovered by a lot of people. So now we have this C star integration, and this C star integration will work when you have steady state situation, prevailing steady state situation. When you don't have steady state situation, so when you have situation where elastic stresses, elastic strains are also there, so like you did for constant displacement test, you see that with time what happens, elastic strain decreases, creep strain develops. Okay, so when we have a crack situation, then initially there can be a plastic zone, there can be a deformation zone which is formed because of time independent phenomena, and you will have a creep zone. So a time dependent deformation will start increasing, although there is no clear cut boundary between these two, because really dislocations are moving and then they start climbing. So there is no physical boundary there. Okay, but this physical boundary will appear when the times are longer, so that the time dependent deformation is crossed. How this will become a physical boundary? The strain hardening which will be happening will be different for time dependent phenomena and time independent phenomena. Okay, so if you take hardness, if you load that sample and stop the test in between, and you should stop the test when you expect that the creep zone is larger than plastic zone, and then you take hardness in this area, so you will see two different regions with two different hardness, because they are deformed to different levels. One of the zone is deformed because of plastic deformation, which is time independent, and another is deformed where a little bit of relaxation has happened. So it is a little bit softer. Okay, it follows a different equation. And then with more time, you will have a situation that where whole of your sample, most of the sample, we are not bothered here, because at holes we really don't want stresses to go beyond elastic. We don't want to do that, and that will never happen, because that part is not connected. Okay, so whatever load you are applying will be transferred to the tip, because it will act like a hinge. Okay, so at one situation you will have the creep zone which will engulf the whole sample, and everything will be deforming plastically because you don't have to increase the load. Basically what is happening is that material is getting viscous with time. Material is becoming softer. Steel is becoming chocolate. That is what is happening. So from here we'll discuss. Do we have class tomorrow?
Yeah.
Yeah, we'll discuss that. You can start.